go over the first couple until we get to part 2, and also question 4 or 5 will go a bit more detail. So how is the skip list constructed? So firstly, it contains multiple layers. It contains a bottom layer, and then it may increase to a level 1, level 2, depending on the variability of your list, and also the your nodes, and yeah. Anyway, sorry. So let me dive into it. So each level higher is sparser than the subset, or than the bottom layer. The bottom layer will contain all of the numbers or values or nodes, and then each level up. So we got level 0 contains everything. Level 1 will have a few less. May contain some though. Level 2 will be even sparser, and so on, so on, so on, until we've kind of got some towers going of certain values. So nodes at higher levels kind of help skip over the nodes below it for faster access. Yep, so what does each linked list store? So they store a key value and forward pointers. So a node with a height of h, this will have h forward pointers, if that makes sense. And also, as it says here, each list level is sorted. The height of the skip list, this is determined probabilistically. Oh my gosh, probabilistically. I've tried to say this word like 3 times, and I'm just gonna run with it now. I've done 2 row recordings, and anyway. So a way of just doing this, and what we've done for this task is using a coin toss. So each new node starts at level 1, and the coin toss is done repeatedly. So H will add a new level when it's heads, a new level is added, and then tails, it stops and it inserts. And then it goes again for the next one. So, this simulates like a geometric distribution, which is random as well. So the time complexities and skip lists and other stuff like that. So, for search, that's the operation, obviously, search, insert, and delete. The expected time complexities for all operations is 0 log n. This happens because the skip list, it uses like a randomization to build a balanced structure, where each level skips over more of the nodes. Skips over more nodes. So the operations don't scan all the elements. They kind of jump through the higher ones and then drop down when they're needed. Kind of like binary search as well. So the expected time in this context kind of means the average case, assuming the randomness is, coin tosses, and they behave normally as well. So it's a 50-50 chance. So on average, insert, search, and delete, they take O log n time. This is different from the worst case. In the worst case, the skip list would behave like a normal linked list. So if the random tosses are unlucky, or if they're like all tails or all heads, everything ends up. All tails in this case. Everything ends up on level 0, and then you'd have to scan all the elements. So again, that's very unlikely, but that's the worst case. So then it's a constant line of 1 to 10, where this has your nodes above, where we can kind of pinpoint what we've got. All right, so the skip list and other structures. So here we compare like your arrays, your single linked lists, and your double linked lists, and also the skip list as well. So, I'll explain the skip list majorly. So the advantages of it. You've got your fast search. Actually, no, I'll probably go into it a bit. Yeah. So, firstly, for the skip list, you've got well, the sorting required. It maintains the order. So, it's also flexible, so it's easy to grow, and extra space can be added, meaning it can be balanced as well, in the skip list, for your search. Sorry, we've got olog n here, which is expected because that's the expected thing we've just realized in this one. Yeah. Also, your advantages with the skip list: you've got faster search, insert and delete. But that's obviously that's on average. Sometimes in your less probable cases, it could take longer because your worst cases become a reality and they actually happen. And you can also dynamically adjust the height without having to rebalance it, which is good. And I guess some disadvantages of the skip list that it uses randomization, so you can't guarantee the worst case or the best case performance, and you're slightly more memory required, overhead, whatever you want to call it, because of the multiple forward pointers per node. That's per value or per tower in our case. Potentially meaning it's slower than other arrays, for like reading access. So next, I guess I've kind of gone over that, haven't I? No, so what I'll do, sorry, I've got the hiccup. So I'll go discuss part 2 now. This took a while to wrap my head around, which I guess it was like the main ordeal. But I'll skip down here. We've got I went onto Anaconda and I just programmed this but onto a graph because this was hard to read, so I just did your skip list, of course, and we can see we have our tower heights or our nodes of each on the x-axis, and then the tower height on the y-axis, and then the values on the x. Yeah, so according to the HT sequence, or the heads and tails, we've got when H is flipped, the height increases until T is flipped, then it will cut it at that level. So here we had, alright, T, I think it was H, T was flipped on the 1, so we've got level 0, moves on, H, we go up 1, then T was flipped, bam, then T was flipped, I think, then bam, then H, cool, we'll go up 1, H, we'll go up again, yep, and so on. So that's kind of building our skip list, and then when we we search, then we can search from level 2 or level 3 in that case, and we can pick OKU, OKU, OKU when we're searching. So yeah, the height of the tower, kind of the more levels it participates in, helping with faster search, as I said. So that's that. This is the same thing, just represented with numbers, sort of. So yeah, sweet. Thank you.